So this is the FutureHacks Robotics Workshop, and my name is Harsh Patel. Okay. So quick question, what do you guys think robotics is? Like any answer, what do you think it's about? What does it incorporate? What do you guys think it is? You can type in the chat or you can, unmute yourself and answer the question. What do you guys think?
Making machines that like solve problems and stuff.
Yeah, basically that's what it is, right? Robotics, making machines. Anybody else? Okay. Okay, so what is robotics? So robotics consists of three parts. So as you can kind of tell by these little icons, it's mechanical, electrical, and then programming. So it's mechanical, electrical, and then computer science. If you incorporate all these things together, you guys can make a robot. You guys can work in the field of robotics, right? Sorry, there's just more people joining. Okay. So how do you go to the next slide? Okay. So what is mechanical engineering? So mechanical engineering involves engineering dealing with design, construction, and use of machines. That's what the dictionary says. Basically, that means that they are responsible for anything that physically moves, right? So you can think of physical objects like that. And in our case, the parts of the robot you can see. So in our case, the mechanical sector has to solve many problems ranging from moving the robot to the robot moving other things, right? And it's not concerned about how to control movement, only that when a motor is powered, the mechanism will work. So basically, for example, let me try to get an example. Like gears, right? These are, you can think of them as the mechanical section of the thing. If I just keep them by themselves, they're not moving. But once I incorporate the electrical side of this, once I connect like something like a motor to it, they can move. So now this is where we get to electrical engineering. So electrical engineering is an engineering discipline concerned with the study, design, and application of equipment, devices, and systems which use electricity, electronics, and electromagnetism. Basically, that means they are. Someone else trying to join. Basically, that means they're responsible for controlling electrical energy. So in our case, it could be powering motors, using sensors to detect certain things. And yeah, and then computer science is the last part. So we have all these machines. We have this electrical side, we have this mechanical side, but how do we incorporate them together? Like, how do we tell the motor when to run, how fast to run, what controls that? So we control that with code. So in our case, that means creating, for example, autonomous systems that can reliably allow the robot to perform tasks on its own. For example, if you have a sensor, you can tell it, oh, run the motor when something specific happens, like when the object in front of you is the color blue, you can use a color sensor or something like that. Or when you move a certain distance, then maybe rotate right or something like that. You can use sensors and you can use motors and control these electrical systems, which then propel the robot to do something, right? So yeah, that's what it is. Okay, so now we're gonna talk about mechanical concepts. So a lot of this workshop is just going into like the mechanical part of robotics. So we're going to be talking about like different systems, different types of machines that are used commonly in robotics. Sorry, just letting people. So this is like a beginner course. So we're going to go through some beginner systems that are commonly used in making robots. Yeah.
They have already started.
Sorry. Okay. Okay. So first things, what are actuators? So actuators are any device that converts energy, whether that be electrical, air, hydraulic, into motion. Without actuators, a robot would just sit there. So for example, what are some types of actuators you guys think are on a robot? So what are certain devices that can convert energy into motion? Any type of energy. Just name some. Any type of actuator. Think simple, don't overcomplicate.
Motors?
Yeah, motors, right? Basically, we power electricity to it, and then the motor spins. It converts electrical energy into motion. Anything else? That's basically like the main one, but there could be other ones. think of something that might use, for example, air into motion. This might be a little bit harder, but
Hydraulics.
yeah, that's water into thing. But yeah, that is also an actuator, right? So let me go exactly, right? So electric motors, how it works, they spin when powered. The common user for wheels, arms, small robots, stuff like that. And then there's linear actuators. This pushes or pulls in a straight line. So I'll actually show you a cool example of a linear actuator in real life. I have my 3D printer right beside me. So I'll show you that. And then pneumatics uses compressed air. And then hydraulics uses liquid pressure. So pneumatics and hydraulics are similar in terms of where they use compressed fluids to work something, right? So these are just a few examples. As you can see, there's a DC motors, and this is what a linear actuator is. So there's, in terms, I'm going to be talking about linear actuators a little bit, but linear actuators are basically, they use a motor and convert it into linear motion. So there's 3 ways that can happen. First of all, you can use a motor and then you can connect it to a lead screw, which is just the type of screw that allows it to go like up and down. You can connect it to a belt or you can connect it to a chain, something like that, right? Okay, so before we move on, I just want to show you an example of a linear actuator in real life because you might not often see it, right? So 1 second. Can you guys see that? Thumbs up if you can see that. Sorry, my leg camera's kind of blurry. Okay, so a cool example of a linear actuator is this right here. So, sorry, I don't have a phone on me, but as you can see, there's a motor powering it right here. This is a stepper motor. And basically, this little nozzle right here, this is what spews out the filament, the plastic, moves along this linear motion, right? And then there's also, then there's also this right here, this bed, which goes forward and back using another motor, which is connected to a belt. So that's an example of a linear actuator. Another good example of a linear actuator uses a lead screw. So as you can see, there's a screw here. And once by rotating a motor at the bottom, I can cause this whole gantry to move up and down. So those are some examples of linear actuators. Okay. So we got through the basics a little bit. Now let's go to levers. So a lever, sorry, 1 sec. A lever is a simple machine that helps you lift or move a load with less effort by using a rigid bar and a pivot point called a fulcrum. So levers are used very often in robotics, and the main purpose of a lever involves mechanical advantage, which is the ratio between the amount of force produced by the machine to the amount of force applied. So to be mechanically advantageous, you want the output force to be greater than the input force. You want to put in less force and get a greater output force for it. And how do we do that? So let me zoom in again. Okay, so how do they work? You apply a force on one side to move something on the other side. The position of fulcrum changes how much effort you need. So as you can see, they're supposed to be mechanically advantageous. So in order to get a mechanically advantageous system using a lever, you want less force applied than the output force. So how do we do that? How we can do that is as you can see from this, let me bring out a pointer. Oops. Can you guys? No, you can't see my mouse. 1 sec. Okay, laser pointer. Okay, so as you can see, this is the force applied and it's moving this load. In order for me to apply less force, what I can do is this side of the arm can be longer. And you can kind of think of it like a seesaw, right? The farther you are from a seesaw, the longer the distance you're applying the force, but the less force you have to apply. If, for example, the force being applied was like right here, you would have to apply a greater force, but across a shorter distance. So if you're applying a greater input force, then the output force, it's less mechanically advantageous, but you're moving a shorter distance, right? Okay. Okay, levers, the three types. So there's three types of levers. There's a first class lever. So three aspects of a lever include the load, the effort, and the fulcrum, right? So effort is where you're applying the force. Load is the thing you're trying to lift or move, and then fulcrum is the pivot point. So for our first class lever, the fulcrum is in between the effort arm. So this side, the part of the lever, that's where the effort's being applied, and the load arm, right? So that's the first class lever. A common example of that is like a seesaw, right? A second class lever is where the load is in between the effort and the fulcrum. And the third class lever is where where the effort is between the fulcrum and the load. Okay. Okay, so the three class levers. So the first class lever is sometimes mechanically advantageous. The reason being is one sec, sorry. The reason being is it dependent on how far close to the fulcrum you are applying an effort or applying an input force depends on how much the mechanical advantages. So for example, if you're applying an input force or applying an effort really close to the fulcrum, that means you have to apply more force for a small output force. But if we apply a force, an input force, an effort force farther away from the fulcrum, then we have to apply less force. So depending on how far you are applying the force, how far your effort force is from the fulcrum, depends on if your system is mechanically advantageous or not, right? So that's why I wrote sometimes for first class levers. Second class levers, however, are always mechanically advantageous. The reason being, as you can see here, the load is in the middle, right? And the effort is farther away from the fulcrum, the pivot point, than the load is. And since you're farther away, you apply less force than the load is applying, right? And since the load is always in the middle, that means the effort is always farther away from the fulcrum than the load is. So you always apply less force for a greater output force. Does that make sense? Any questions so far? No, good. Okay. And then third class levers is where the effort is in between the fulcrum and the load. So if the effort's closer to the fulcrum, the distance is shorter, that means you're applying a greater force. And since you're applying a greater force than the amount of output force you're getting, that means it's a mechanical disadvantage. And it's always a mechanical disadvantage. Any questions so far? Does anybody have any questions about why certain things are certain ways? Like why do you have to apply more force, a greater or less of a distance, or anything like that? Yeah. Yeah, what's your question?
So can you give us another example of a third class lever? Because I still kind of don't understand it.
So do you get the bicep image? Or let me think of another third class lever. Being a fishing, yeah, a fishing rod is also a good example. So if for example you have this is my drumstick, but like if you have this is the part of the fishing rod that's pivoting, right? And you're pulling on it from here. So you're applying an effort in the middle and the force is here. So this is your fish over here. This is a load. And you're trying to pull it this way, right? So since you are the effort is in middle between the fulcrum, the pivot point, and the load, you have to apply a greater force than the output force that you're gonna get out of it. Does that make sense? Do you understand the reasoning behind it?
A little bit.
Okay, let me try to explain it more. Have you ever you guys have been on a seesaw, right? the farther you are away from the point that pivots, like the rotating point, the less force you have to put on it, right? The reason being is, let's say you have a first class lever, right? This is your seesaw. If I'm farther away from it, I'm moving a greater distance, right? Since I'm moving a greater distance, let's say I apply like 5 newtons of force, right? Across this huge distance. Since I'm moving a greater distance, I'm applying a greater amount of force across that whole distance. So let's say I move 5 meters, I apply a certain amount of force, like 5 newtons. Since I'm applying it over a greater distance, I don't want to go into more like energy terms, but I'm just kind of simplifying it. That means I have to put in less force because it's over a greater distance, right? Like, for example, if I was here and this is the pivot point, it takes more force to make this end go up, this load arm go up, because I'm applying it over a smaller distance. I'm moving this part of the stick over a smaller distance because it's closer to the fulcrum. If the farther it is, the easier it is to move. Like if I go here, it's harder to move. Does that kind of make sense? Okay, I'm gonna take that as a yes. Okay. Let's go on to the next slide. Okay. So now we're gonna do a little bit of examples. So let me just, how do I get out of here? Okay. So we have this lever right here. So I want you guys to tell me first what type of lever it is, and if it's a mechanical advantage or not. And then you're gonna tell me why it's not a mechanical advantage or if it is a mechanical advantage. So first, what type of lever is it? So this is just color coded. So the load is on the left, the effort is on the right, and then the fulcrum is in the middle. So what type of lever is it? What do you guys think?
First class.
First class. Okay, good job, good job. So let's check, see if we're right. Okay, boom, we're right. Now, mechanical advantage. What's a mechanical advantage? Do you think it is a mechanical advantage? Do you think it's not a mechanical advantage? And for these two examples, just imagine they're the same force, okay? Or they're like the same. Yeah. So is it a mechanical advantage? Yes, no, or neither.
I think so.
Okay. You think it's a mechanical advantage? Why do you think it's a mechanical advantage?
Because you said the farther away it is from the focal point, the more advantage it is, and it's like as
Yeah.
far as it could get.
Yeah, that's good.
Are
So-
we talking about the first one?
Yeah, the first one. This
Oh.
one right here. So what do you think, Isaac? Is
I think it's neither, since both of them are same distance from each other. So
Yeah,
if
exactly.
four, they would equal out.
That's good, exactly, right? So I agree with Isaac too. I think it's neutral. The reason being is both of them are the same distance away. In order for the first class lever to be mechanically advantageous, right? Remember in the slide, it said sometimes it's also only mechanically advantageous. The effort has to be farther away from the fulcrum than the load is. In this case, it looks like they're the same distance away. So that would mean that they're neutral, right? If you're applying a force on one side and it's the same distance away as the load, then the output force will equal the input force if you assume it's a perfect system and there's no like friction or whatever like that. So in this case, it's neutral. Okay, good job, guys. Next slide. Okay, so what type of lever is this now? So the effort's on the right, the load is on the left, and the fulcrum's in the middle. What happens when the fulcrum's in the middle? What type is it?
Second.
First class, right?
Fulcrum's in the middle. Think. If fulcrum's in the middle, what type of lever it is? Think of a seesaw.
First class.
What type? First class. Good job.
Oh, first.
So yeah. So anytime it might look like, oh, it's different from the first, but in this example, the fulcrum is still in the middle, right? Whenever the fulcrum's in the middle, it's a first class lever. And this time, is it mechanically advantageous or mechanically disadvantageous? Advantage. Okay, I don't know English. But yeah, is it a mechanical advantage or a mechanical disadvantage?
Advantage.
Advantage. Why is it an advantage?
Because there's like a bigger difference between the effort and the fulcrum.
Yeah, so in the effort, since you're a farther distance away, you have to move a larger distance, but you put in less force to get a greater output force. Okay, good job, guys. So let's just see if we're right. Okay, we're right. All right, next one. Okay, this one's a little harder. I'll give you a hint. It's not a first class. So the load is in the middle. The fulcrum's all the way on the left, and the effort's on the right. So a good example of a second class lever is like a wheelbarrow. So what do you guys think? Have you guys picked up a wheelbarrow before? It's like really easy, right? You can have like a bunch of dirt in it, but it's not too heavy compared to how much dirt you're picking up. So what do you guys think? Which type of lever is that?
Second class.
Second class. Okay, good job. And based on me giving that example of dirt for some reason, is that a mechanical advantage or a mechanical disadvantage?
Advantage.
And why is it advantage? I know it's a second class lever, but why?
Because
Just
the
think.
effort is farther away from the fulcrum.
From the fulcrum.
Yeah, so it's farther away from the fulcrum than the load is. So farther away, the less force you put. The less force you put, you're doing a good job. You're being mechanically advantageous. So yes, you guys are right. Okay, this one's a little bit easier. What type of lever is this?
First class.
First class. Okay, I think everyone's caught up now. And then is a mechanical advantage or disadvantage?
Disadvantage.
Why is it disadvantage?
Because the effort is closer to the fulcrum than the load.
Okay. I think everyone's got a hang of it now. Okay. All right. Okay, this one's easy too. What type is it?
First.
First. Okay. Isaac's on a roll. Okay, mechanical advantage or disadvantage?
Advantage.
Okay, yes. Okay, Isaac knows his stuff. Okay, type. Okay, this one's also easy. This is like the normal one. Sorry, I didn't hear you.
First class, right?
First class. Okay. And mechanical advantage, disadvantage, which one?
Disadvantage.
Yep. Good job. Yeah. What about this one? This is slightly different. I think
Second
we've done
class.
this. Second class. Okay.
And it's advantage.
So, okay, quick question. Is a second class lever always an advantage or is it always a disadvantage?
Always an advantage.
Why is it always an advantage?
Because the effort is always farther away.
Exactly. And then type, oh, what type is this? Oh, this one's slightly harder. So the effort is now in the middle, the fulcrum's on the left, and the load's on the right. This is like the example of the bicep. Yeah,
the third one.
the third one. Okay. Yep. Advantage, disadvantage,
It's always a disadvantage
disadvantage. Why is it always a disadvantage?
because the effort will always be closer to the fulcrum than the load.
Yep. Good job, guys. Okay, last two. Which one is this? Efforts in the middle.
Third class.
Third class.
And it's a
Which one?
disadvantage.
Yep. Okay, everyone's on our roll. Okay, last one.
First.
What is first? Okay, this is kind of a trick now. Is it advantage, disadvantage? What is it?
Disadvantage.
Why?
Disadvantage, actually, I think it might be neither.
Neither? Why is it neither?
Since they're same distance.
Yeah. It's neutral. Like you can think of it like a seesaw, right? I know some seesaws have like different parts of the seesaw you can sit in. So you might think, oh, like what about all this extra length on the effort side? Like, isn't it farther away or isn't it farther away? So shouldn't it be like mechanically advantageous? It shouldn't be neutral, right? But since they are the same distance, since the point where you're applying the force is equal, it's neutral. Okay, now we're gonna do some math. It's not overly complicated, but basically based on the force and the distance of each side, the effort arm and the load arm, we're gonna figure out the distance or the force or whatever it is. So we have two equations here. So we have force one, so the force of the effort and the distance away from the fulcrum that the effort is applied, and then F2 is the force of the load, and then the distance away from the fulcrum the load is. So that means that the further weight is placed from the fulcrum, the more force the other end of the lever experiences. However, the further from the fulcrum that, okay, I did not write this properly, that will translate, the further that the fulcrum, okay, what did I write? However, the further from the fulcrum, that movement will translate to less move, okay. I don't know what I wrote, okay. But basically, the farther away you are from the fulcrum, the less force you need to apply. I don't know why I overcomplicate. I don't know how to rate. Okay. Okay, let's get into some questions. So I'm gonna do this one for you guys, and then you guys can get a little bit of a hang of it. So the first question is, how much force would it take to balance the load? Okay. So if we're gonna balance the load, we want the thing to be flat. So we want the left side to equal the right side in terms of force we're applying, distance it's doing. So that's where this equal sign comes in, right? The left side or the effort side equals the load side. And that doesn't just mean force, that includes force and distance. So what's the question asking? So how much force would it take to balance the load? So in this case, I made the load green. Okay, so the question mark is the force. Okay? Okay, my light, can you guys see that? I don't have an online whiteboard. Okay. So basically, let's just write out all their values. So for F1, that's effort, right? We don't know that. Do you guys see that? Or is it like flipped for you guys?
We can see that.
Yeah,
Okay,
we
you can see. I'll make it bigger. It's a question mark. Okay, we don't know that. Distance one, the distance away from the fulcrum that the effort is 10. So we're working with meters, so 10 meters. And then distance two is also 10 meters. And then F2, so the force of the load is 5. Is it 5? Oh, it's 5 kilograms. Okay, so I don't think 5 kilograms. Okay, so let me go on to the next slide. So kilogram is a unit of mass, not force. So it gave us 5 kilograms, but is this a unit of force? What's a unit of force, if you guys know?
Newtons.
Newtons, right? So this is where we can use force equals mass times acceleration. So to convert mass to force, we use this equation. So if the mass is 5 kilograms, the acceleration on Earth, specifically on Earth, is 9.8. So for example, if I had this stick was 5 kilograms, and the acceleration is 9.8, right? Because we're on Earth. I would need 49 newtons of force to keep it neutral, like prevent it from falling. If this was 5 kilograms, it's not 5, but if it was, right? So in these questions, we're given the questions in math, but we have to, oh, that just ruined the answer. Okay. We have to convert it to newtons, right? So I'll convert this one to newtons. So I'm going to times it by 9.8. That is 49 newtons. Should write my units. 49 newtons, okay? So now we can solve for the first force, for the effort force. So force 1 times distance 1 equals F2 times distance 2, right? So we're solving for force 1. So what I like to do is I like to isolate for force 1 and just keep all of the known values on one side. So we're just solving for the unknown. So I'm going to divide both sides by distance 1. Cancel, cancel. Force 1 equals force 2. Okay, this mark is dying out. Do I have another one? Okay, I might have another one. Okay, yeah, that's better. Force 1 equals force 2 times distance 2 over d1, right? So now we can just plug our values in. And we get force two, which is 49 newtons times 10 meters divided by 10 meters. So you can plug in this into your calculator, but I can just see this 10 cancel out with this 10. So I'm just going to cancel these out. And what's my final answer? If those two cancel out.
49.
49, right? And also the units also canceled out for the distances. So I'm left with the unit 49 units. And that kind of just makes sense, right? If it's a first class lever and the distances are the same, then you have to apply equal forces on both sides for the lever to be neutral, right? So that just makes sense. Okay, so let's see if I'm right. Think I'm right. Okay, I don't think I'm right. 400, what? How much? Oh, how much force have you moved it? Okay, let me see if this is right. Okay, 10. And okay, how much would the load move if the force moved? Did I do this right? How many people are coming in? Okay, give me 1 sec. Sorry, 1 sec. Yeah, I think I just made a mistake on that one. Yeah, so many tabs. Okay, let's. Oh my God. Okay. So you got the answer right there, but let's try to answer the question. So how much force would it take to balance the load? So I want you guys to try this on your own. Just get a piece of paper out and remember that this is 17 kilograms. So you got to convert it to for newtons. So you got to use the equation of force equals mass times acceleration. And you're trying to find out how much force it would take to balance the load. So I want you guys to try that out. Then let me know what you get. Okay. So anybody try it so far? You guys understand it, or do you want me to go over it one more time?
Are the 17 and 3 the distance or the force?
Yeah, so this three at the bottom, like the 3 and 17 are distances. So it's 3 meters and 17 meters. And then the green arrow, 17 kilograms. So you got to convert it to force.
Is it 944?
944. Okay, let's see. We got that right. Yep, 944. So I'm gonna walk you guys through it. So your first, you don't know the force, right? You know the distance one is 3 meters. You know the force two is 17 kilograms, but you gotta convert it to newtons. So force, so it's times 9.8 meters per second, which is 166.6 newtons, and then your distance two is 17 meters. Okay, so you're gonna try to solve for force one. So that's a D. So I'm just gonna isolate for force. So F2 times D2 all over D1. So force one equals 166 newtons times distance two, which is 17 meters, all over 3 meters. So let's see what do we get for that. So yep, if you guys can see that, 944 rounded is 944. There's a bunch of decimals at the end, but yeah, 944. So let's read the second part of the question. So how much would the load move if the force moved 15 meters? So how much would the load move if the force moved 15 meters? So it's asking us if the effort arm, if the distance of the effort arm moved 15 meters, so now it's 15 meters, what would the force be? So how much would the load move if the force moved 15? So all the other values are the same, but now we're solving for D2. So F1 is still 944, that's a 4, 944 newtons. D1, 15. And then, what's it called? F2 is 166.6. And then D2, we don't know. So how would we go about solving for that? So I guess I want you guys to try that out real quick. And then let me know what you guys get. Oh God. Okay. What'd you guys get? I know I accidentally showed the answer, but what'd you guys get? If you guys tried to solve for it. Okay, I'm just gonna go through the problem. So we know what about we mark it? Okay. So we're solving for D2 now. So we have D1, F1, F2, but we don't know D2. So we're gonna isolate for D2. So get rid of that F2. And we had F1 times D1 over F2. It's kind of cutting out, but equals D2. So D2 equals equals 944 newtons times 15 meters over 100. Oh, yeah, 166.6 newtons. So what do we get? Let's try plugging it in. You get 85 around approximately. That's your answer. Okay, so I know this math is kind of boring, I'm gonna be honest with you. So let's just skip through this because you guys are pretty smart, so you already understand most of this. So let's go to gears. Okay, so we're getting into the fun stuff. So what are gears? So gears are basically just wheels with teeth that mesh together to transmit motion and force, right? So when one gear turns, it makes the other gear turn too, but in the opposite direction, either faster, slower, or in a different direction. So I have a good 3D printed example of this. You got two gears here, right? When this gear moves, so that just broke apart. When this gear moves, the other gear moves. Right? If I rotate this clockwise, the other one moves counterclockwise. And I also mentioned it can either make it move faster or slower. So if I rotate this once, this moves twice. And we'll explain why that happens too. So there's different types of gears. There's spur gears. These are kind of just like your regular gears. Like these are spur gears. There's bevel gears. That's a spur gear. There's bevel gears. This one right here, which is basically is when you want to connect two gears at an angle. So one is like horizontal and one's vertical. You can do that with when the teeth are 45 degrees like of an angle. There's worm gears. And then there's spur gears, which are for linear motion. So this is another example of where you could use a linear actuator also. Okay, so gear ratios. So in terms of the part of the description where it said you can either make it move slower or faster, that depends on your gear ratios, right? So if one gear is bigger than the other, it can cause a different number of rotations for us. So for example, if this is the gear I'm moving, like I'm putting a force into, since this has, for example, 30, I'm pretty sure this has 32 teeth and this has 16 teeth. For one rotation of this moves two rotations. And the reason being is because of the number of the teeth. So this is a driven gear. This is a gear we're like inputting force into. And this is the driver gear. This is like the output gear. Since this has 32 teeth and this has 16, we can use this equation. So the teeth of the driven gear is 30. Oh, driven gear, this one right here, is sorry, is 16. And then the teeth of this gear is 32. So 16 to 32, that's 1/2, right? So the driven gear is basically just the output gear. And the driver gear is the one that you're like, you're actually applying a force to it. The driven gear is the output force, like the output gear, right? So this example here with 50 teeth to 25 teeth. So the teeth of the driven gear to the teeth of the output or the driving gear. So 25 to 50. So it's 1 to 2. So basically, if I move the big gear once, I'm gonna move the smaller gear twice. Rotate it twice. So let's do some little bit of math. Okay. So let's say you have the teeth on your driver gear. That's the gear you're like inputting a force to is 15, so it's small. And the teeth on the driven gear is 45. So what is your teeth ratio? What's your gear ratio? What do you guys think that is?
1/3.
1/3, right? 15 over 45, 1 to 3. And what about rotations of driver gear? So let's say I rotate the smaller one 27 times. How many times is the driven gear, like the bigger gear, gonna rotate? So if it's 3 to 1, that means, or 1 to 3, if I rotate, oh sorry, yeah, 3 to 1, then how many times is that gonna rotate? It's 1 to 3, sorry. So if you rotate it 27 times, how many times is the other gear gonna rotate? So it's
81.
oh wait, sorry. It's wait, who said one? Did it say 1 to 3 or 3 to 1? Sorry, it's 3 to 1. So the smaller gear, it's driven over driver, right? Or sorry, driver over driven. So if you rotate, sorry, if you rotate the smaller gear 3 times, you rotate the bigger gear once. So if I rotate the smaller one 27 times, how much is a bigger gear gonna rotate?
9 times.
9 times, right? 3 to 1. So 45 over 15, 3 over 1. So next question. The teeth on the driver gear is 45. And the teeth on the driven gear is 15. So what's the ratio? How many times will I have to rotate that big driver gear to rotate that smaller gear? So 1 revolution of the bigger gear equals how many revolutions of the smaller gear?
3.
3, right? So our ratio is 1 to 3. For 1 rotation of the bigger gear, I rotate the smaller gear or the driven gear 3 times. So now let's say I rotate that big driver gear 65 times. How many times am I gonna rotate that smaller gear? Since it is a smaller gear, it has less teeth, that one will rotate more. So that's a hint if it's 1 to 3.
195 times.
195, yeah. So 1 to 3, 15 over 45, right? And the next one, you have a smaller gear, it's 15 teeth, and then the bigger gear is 75 teeth. So what's a gear ratio for that one?
5.
5, right? So if I rotate the driver gear 5 times, I rotate the driven gear 1 time, so 5 to 1. So now if I rotate the driver gear 12 times, how many times am I gonna rotate the driven gear? 5 to 1, so 12 to 1.
60.
60, okay. Close, I get where you're getting at, but basically, the smaller gear is gonna rotate 5 times to rotate the bigger gear once. So the smaller gear always rotates more than the bigger
Two.
gear. To what would you guys say? 2 point what?
2.2.
Okay, let's see what we got. 2.4. So 12 divided by 5 is 2.4, right? Make sense? Okay, next one. So you have the driver gear having 75 teeth and the driven gear having 15. So how many rotations of the first gear will lead to how many rotations of the second gear? How many rotations of the driver will lead to how many rotations of the driven?
1 over 5.
Mm-hmm. And then, so basically 1 rotation will lead to 5 rotations of the driven gear. So now if I rotate the driver gear 45 times, I rotate that big gear 45 times. How many times is the smaller gear, the driven gear, going to be rotated? Remember, it's smaller, so you're going to rotate it. It's going to rotate more because, right, no, it's smaller.
225.
225, yep. Okay, this one's slightly harder. You have the driver gear rotating with a number of teeth as 45 and the driven gear having 75 teeth. So what is the gear ratio? This one's a little harder.
3 over 2.
3 over 2, yep. So I rotate that small gear 3 times. I rotate the driven gear 2 times. Okay, a little bit harder. I rotate the driver gear 82 times. How many times does the driven gear, the bigger gear, rotate? So since it is the bigger gear, it should rotate less because it has more teeth. So what do you guys think? How many times is that gonna rotate?
55 times.
5 times? It's gonna rotate 5 times?
55.
55? Okay, let's see. Okay, maybe I did my math wrong. 82. So I rotate that gear 2 times, and it results in that other gear rotating 3. Yeah, I rotate the smaller gear 3 times, and it results in rotating the bigger gear 2 times. Okay, maybe I just wrote it wrong. Yeah, I probably wrote it wrong. Yeah, you're right. It's 55. It's 55, 54.69 or whatever, but oh, okay. Next one. You got the big gear, you got the driver gear being 75 and the driven gear being 45. So what's the ratio? Same thing as the other one, just flip it.
2/3. Is it
2
2/3?
2/3. Not 2/3. Wait, is it? Not exactly, but no, not exactly. Wait, is the other one? Who said 3/2 for this one? 75/45. Yeah, the other one's not 2/3 either, but wait. Okay, then that one might be wrong. Now let's check it back. 75/45. If you divide both by 5, let's divide it by thing. 5 divided by 45. It's 5/3. Okay, yeah, so maybe, yeah, I was wrong with that one. It's 5/3. So I know we know the answer, but like, let's try to solve it, right? So we know there's so much stuff on my whiteboard. Let's try to think of this. Okay, so 75, yeah, 75/45. So that ratio is 5/3. Yeah. Yep. Yeah, 5/3. So that means if I rotate this gear, the driver gear, 82 times, 82 times, how many times is the driven gear going to be rotated? Can you guys see that? It's like the shadow. Okay. So you can think of this as fraction. So 5/3 over 82 over x. You can either bring the x to that side and then bring that over. What I like to do is just do the reciprocal. So 3/5 equals 7/82. Isolate for x. Times both sides by 82. So 82 times 3 divided by 5. So it's 49.2 is x. So 49. Close enough. So if that's 5/3, then what's the second one? Because it uses the same number of teeth, but now you're just flipping the driver gear to the driven gear. The old one was 5/3. So what's this new last one? What's the ratio? 3/5, right? So 45, 75 is 3/5. So the ratio is 3/5. And you're rotating the driver gear 77 times. So how many times are you rotating the driven gear? So 3/5 equals 77 over x, which is the number of times you're rotating that one. 5/3 goes, yeah, my markers are running out. Try to use another one. 3/5 equals 77 over x. So 5/3 equals x over 77. Isolate for x. 77 times 5 divided by 3 is 128. Approximately, it's 128.333. But yep, that's it. Okay, so let's talk about some cool mechanisms now. So these are compound gear trains. So as we saw, if we connect a bigger gear to a smaller gear for one rotation, it can lead to more than one rotation of the smaller gear. So that can cause this output gear, that can cause a driven gear to rotate to be faster. The reason being is in a shorter time, it's moving more revolutions. So let's say this gear takes 1 second to rotate once, since it's a 1-to-2 ratio, that means in 1 second, this gear rotates twice. So it's faster, right? So sometimes you want to use compound gear trains to change up the speeds of the output gear dependent on what you're connecting it to. So this is a cool example. So let's say you got this big gear, right? And then you kind of attach another smaller gear to it. This causes this idle gear, the idle gears are like the middle gears, to rotate slower than it would have if you connected it to this big gear. The reason being because this ratio is 1-to-1. So for example, if this big gear was connected to this idle gear, the smaller gear, if it rotated once every second, this would rotate, for example, 2 times every second if it was a 1-to-2 ratio. But since it's a compound gear, it connects another smaller gear to it. This makes sure that this ratio of the idle gear is still 1-to-1. So it'll only rotate once every second. So compound gear trains help you decrease the rotations or the speed of the output gear by connecting all these middle gears in front of it. So for example, look at this example right here. So this gear ratio is 10 or 1-to-10, right? 10-to-1. I rotate this smaller gear 10 times. I'll rotate this big gear once because it's 100 teeth to 10 teeth. Now let's look at this one. So this is 10 rotations of this, or 10 teeth here, 50 teeth here, and 100 teeth here. So let's think. 50 teeth over 10 is 5-to-1. So if I rotate this 5 times the driver gear, I'll rotate this idle gear 1 time. And now let's look at this orange gear to this blue gear. If I rotate this orange gear 2 times, I'll rotate this big gear once. So we got 2 ratios going on here. Let me erase all of this. We got 5-to-1 for the, oh my God. We got 5-to-1 for the driver gear to the idle gear, and then 2-to-1 to the idle gear, the output gear. So what's our ratio from the driver gear to the driven gear? What do you guys think that is? I know it's a little bit hard. What do you think that is? How many times will I have to rotate that little small green gear to rotate that big gear? Once. Okay, let's go through it together. So how I kind of like thinking of this is I kind of like getting both the numbers for the number of rotations for the idle gears the same. So right now what I have is if I rotate this driver gear 5 times, I rotate this idle gear 1 time. But if I rotate this idle gear 2 times, I rotate the driven gear once. So what would happen if I made this a 2? How would this number change? So, another ratio that's equivalent, mark with here running go. Another ratio that's equivalent to this is just 10-to-2. If I rotate the driver gear, the small gear 10 times, I rotate the idle gear 2 times. And if I rotate the idle gear 2 times, I rotate the driven gear once. So that means for 10 rotations of the driver gear, I rotate the driven gear once. So it's 10. Does that make sense? Anyone confused? Anyone have any questions so far? No, yes, maybe. No? Okay. So let's go into some cool mechanisms and then we'll go into our Q&A. So cool mechanism. Oh, I had a zip tie with me. That's fine. Cool mechanisms in robotics. So these are just certain mechanisms that I think are pretty cool. So a clutch. So this is like something that's in your car as well, but there's other examples of this, like power drills and stuff like that. So basically, a clutch has 2 parts which engage and disengage. basically deciding when power flows and when it doesn't. So it lets you stop and start motion without turning the motor off. So the motor just keeps spinning, but actually engaging that motor, actually making it move something, depends on if you engage that wheel. So example of like a clutch in a car, there's a flywheel and it just keeps pushing or it just keeps spinning, right? And then there's this mechanism right here that once you connect to it, it'll engage in and actually use the motion of the flywheel towards the car. So for example, the power drill is another example. When you stop pressing the trigger, the motor keeps spinning, but the clutch, I wrote Chuck, clutch stops. And now I think a ratchet is also really cool. A ratchet only allows motion in one direction, locking the other way. Really good example of this is a zip tie, right? I don't have one on me, but a zip tie basically has these little grooves like this. It's not in a wheel shape, but basically has these grooves that allow you to tie it in one way, but then you can't move that part of the zip tie the other way because the grooves, right? If you look here, you can, because it curves to the right, you can rotate this part to the left and allow it to tighten, right? But you can't move the ratchet wheel the other way because it locks that way. That's a good example. A socket wrench is also a good example. Basically, if you like engage it one way, it only moves in that direction. Q&A. Anybody have any questions about robotics? How to get into robotics? What to learn to do robotics? So this was really just a really beginner lesson. There's certain like physics principles and mechanical principles you should know before going into robotics, like the basic ones. But actual robotics involves applying these principles to actually what's it called? Sorry, my mom's phone's ringing in the background. But to actually apply them to actually building the robot, right? So anybody have any questions? Any questions about robotics, how to get into it? What do you guys think? Oh, okay. Any questions? Okay, yeah. Jezreel, hope I'm pronouncing that right. What's your question?
Yeah, good day. Sir, I would just like to ask, where do we integrate the software and those, uh, and the gears and all of those, like the software?
So how do we apply these principles in like real life? Is that your question?
Yep, yep. Where do we apply the software and those?
Okay, so like, apply the software, like how do you connect it to like programming?
Yep, yep.
Okay, so basically, I don't have any examples with me, but a good way to apply these like the software to this is if you connect it. Like I talked about this at the start, but basically, robotics is a combination of mechanical engineering, electrical engineering, and programming, right? You might have all these mechanical parts, but they can't move like if you don't connect them to anything, right? So for example, if you connect it to a motor, you can program that motor to spin at certain points for certain reasons that allow your robot to accomplish a specific task. So let's say you want a robot to move forward, right? You might have a set of gears connecting the motor to a wheel. And once you tell the robot, like, oh, if I move my controller like up or whatever, rotate the motors in this specific direction that connect to these gears, that connect to the wheel, that allow the robot to move forward. So that's a good way of applying it. If you actually want to get into like building your own robots or building cool mechanical parts and stuff like that, a good thing is joining like first robotics team. So FRC, FTC, Lego League, right? That's a place where you can get a lot of like knowledge from. But if you don't have that opportunity, just like learning how to CAD, which is computer aided design, which is like designing all these parts on your computer and then testing them out in real life is also really valuable. But yeah, you can also get like electronic kits like Arduino or Raspberry Pi use all those little sensors, all those little motors, connect them to mechanical parts, make them move and help them perform a specific task, right? So all of them are just parts, but once you connect them together, once you connect them in a specific way, you can reach a specific task. So I don't have a picture. Let me try to, I don't have a picture of my robot, but I might have a video. I don't know, but like I was part of an FTC team, so we had a lot of those like little parts, those gears and stuff connecting to each other to make the robot move or make certain other things happen, like the arm move or something like that, right? Any other questions? Does
Wouldn't
anybody
you
have any
use
questions?
like couldn't you use like PCBs and stuff?
PCBs, yeah. So PCBs, yeah. So printed circuit boards, right? So yes, you can use printed circuit boards to connect them to motors or whatever specific function you have. I'm not really into like the electronic side of robotics that much. I'm more into like the mechanical side. But yeah, you can use PCBs. Like for example, an Arduino is technically like the board itself is a PCB. That chip is what makes the Arduino move like work, right? So for example, like you can actually make your own Arduino board if you make the PCB for it and then just connect the specific chip to it. So yeah, that's a PCB. Anything else? Any other questions? No other questions? You guys have any questions about how to get into robotics, what to do, specifically for mechanical maybe, or anything else? No, yes, maybe so.
So yeah, I do have a question about how to get into robotics like online since I guess I'm in an isolate place in the world. So I wanna know if there's like an online organizations or something that can get me into robotics.
So how you learn robotics. I think a great way is actually trying to get into computer aided design. This is where you can apply these mechanical principles and you can make your own moving parts, right? So for example, I don't have anything on, but okay, I don't have anything on me, but I just have this gear thing on me. I had a claw, but like basically you got these gears, right? This was designed in CAD, right? So I made these gears. This is really basic, but like you can apply these mechanical principles. This is like an example thing, but you can apply these mechanical principles to use computers to design something specific to accomplish a specific task, if that kind of makes sense. And to learn it, I think if you're in like an isolated place, there are probably courses online. But if you just want to get into CAD or computer aided design, like initially, I would think YouTube videos are really helpful. But honestly, just start building something, right? Like think of a project you want to make, like for example, a robotic car or a little RC car, and then just figure it out as you go along, right? Watch YouTube videos, ask on online forums, see how other people can help you, right? That's how you gain inspiration, just looking at other people, what they did, and seeing how you can apply that to your own project, right? I don't have any good examples with me, but I had my robot, but I disassembled it. But yeah, so just look at other people, see what they're doing, see how you can apply that to your own projects. But just think of what you want to build, and then just try to attempt to build it and then learn along the way. I think that's the best. Like learning as you go along is really helpful because that's like the best form of learning. Because you at the end you make what you want to make, and then you learn stuff along the way. So it's a win-win, right? Any other questions or I mean it's 7:10, so it's about to end. But any last questions before I end the workshop? So are you guys interested in robotics? Is there something specifically you guys want to do, and like post-secondary or just right now for fun? You want to get into robotics or yeah, what are you guys into? Like, what are you guys into right now? Like programming, what are you guys into?
Well, I was kind of thinking of like in high school, with on the robotics team building this like you've ever seen those videos where there's like these competitions where they control this robot and picks up these rings and like puts them somewhere?
Yeah, yeah. You're talking about like FRC, right?
Yeah, something like
Virtual.
that.
Yes.
But I
Yeah,
was
that's actually
thinking like instead of a controller, maybe like having an AI, making it move around and think by itself.
Yeah, that's actually cool. So for the robotics competitions you're talking about, like FRC, and then there's like First Tech Challenge, FTC, what they do have is they have like two peers. Like one's autonomous, so the robot moves on its own. It uses sensors and stuff. And the second part is driver control. So there's a person actually driving it with a controller. So yeah, you are right. There are like autonomous peers. There are like AI sections of it that can be used towards robotics to make it autonomous, right? But yeah, I think that's actually a great way. If you can join your like local robotics team or your school robotics team, that's actually a great way to learn because you're learning from people older than you. You're learning from like people who have experience already, and you get to learn hands-on, right? That's like probably the best way to learn. And it's in like a fast-paced environment where you get to learn a lot in a short period of time. But yeah. So if there aren't any questions, I'll end the workshop if anyone doesn't have any more questions. Is everyone good? Yep. Any last questions? I'll give you guys like 10 seconds. Nope. Okay. All right. I hope you guys enjoy the workshop. If you guys have any questions, I think I'm on the WhatsApp for the hackathon, or you can just email me if you have any questions. Let me add my email to the thing. Where's the chat? Okay. Yeah, no problem. Yeah, if you have any questions, just email me. That's my email. If you have any questions about robotics or you want to learn something new, email me. I'll give you some advice if you want. And I hope you guys have a great rest of your day. And hopefully we see each other during the hackathon if you guys are doing that too. My problem. All right, bye guys.
Thank you. Bye.
No problem. Bye.
Thank
Bye,
you.
thank you.
Wait, quick question. Where do I find
Yeah.
more information about the hackathon?
What do you find more information about the hackathon? Like, what do you mean? What's your
Uh,
question?
well, I didn't actually sign up for this. I just got like a random email to join the workshop, so that I did.
How do you
then
sign up?
I got
Um,
in the WhatsApp group, but I didn't see it, and it's like expired. So
oh, okay. So I don't actually run the hackathon. I'm just like doing a workshop, but I can try to find you. I think they have a dev post, like, and then I also asked them, how do I go on dev post? Um, yeah, just give me 1 second. Let me try logging into the hackathon. Uh, okay, yeah, they do have a thing here. Let me send it in the chat. Okay. Do you like know how the team pairing works? I think, I mean, I did the hackathon like a few years ago. Like I organized it like last year. But in terms of pairing, you can work solo or you can work by yourself. You can also ask people if you want to work together or not. It's up to you, right? If you want to work with a partner, you can work with a partner. If you don't know anyone, you can try to look for a partner or you can work on your own. It's whatever. I'm pretty sure that's how they're doing it this year. I'm not sure. I'm not on the organizing team. But yeah. So where do I go look for one? Like look for a partner? You can ask on like the server or whatever. I don't know if yeah, they're doing it on WhatsApp now. But basically on like the community group chat, like, hey, does anybody want to pair up with me or something like that? You can also ask on DevPost. Like if you join through DevPost, there's probably like ways you can pair up with people. Like let me see the DevPost. See how many people are on it. Yeah, you can ask people like, hey, do you want to pair up or something like that? So let's okay, yeah, you already got someone asking you to pair up. Okay, so that you got a partner. But yeah, and then yeah, I also sent the what's it called? The dev posting. And then if you have any questions, also if you guys have Discord, I'll give you the link or the what's it called? The username. Yeah, the username to do you copy this? the username for the someone running it. You can ask them if you have any questions about signing up or something like that. Also, Jezreel asked you if you want to like be a team. So that you got a pair right there if you want that. Okay, any other questions before I close the meeting? Are you guys all good? So yeah, just sign up through there. Yeah, no problem. Okay, bye guys. Have a good rest of your day.